Welcome back. Now we're going to take a look at chapter 21 and learn something about logarithms. Hopefully this will be a review for most of you all. Logarithms is something that we use in AC electronics later when we start looking at frequency response and dealing with measurements of power. So we'll look at the common logarithms, dealing with taking the log of a number, various ranges from 1 to 10, greater than 10, less than 10, and then we'll wrap this all up by looking at multiplying and division using logs, which is a tool for dealing with numbers by using a logarithm, and then looking at natural logs, just briefly introducing them to you. So with logarithms, the thing to understand about a log is it is actually, it's an exponent. It's another way of dealing with exponents and exponentials. So as I said, we're going to look at primarily the common logarithms, but the last section covers the natural log. The common logs are exponents of 10, and handling them, you will see that we primarily deal with the base of 10. Natural logs are exponents of E, and E really stands for something called Euler's. In full electronic engineering, Euler's equations and Euler's relationships get used a lot. It's also called Napier's constant, which has a value of 2.718, rounded off. So what is a logarithm? We can look at it in exponential form or logarithmic form. So if we take an example here, what's the logarithm of 100? The log of 1, typically the way you state it. 100 can be expressed as 10 squared. 10 is the base, 2 is the exponent. So 10 squared equals 100 is our standard exponential form. The logarithm then is the power to which 10, the base, must be raised in order for it to equal 100, the number. So when 10 is the base, we refer to it as the common logarithm. So if we look at 1,000, what's the log of 1,000? 1,000 can be expressed as 10 cubed. Okay, so the base, again, being 10, and now 3 being the exponent. 10 cubed is equal to 1,000, and that's called the exponential form. Hopefully, if you hadn't seen this before, or it's a refresher for you, you start to see a relationship with the number of zeros and what the log is. You'll notice 10 to the third, representing the number 1,000, has 3 zeros. The log of 1,000 in base 10 is 3. So the easiest way to handle logarithms these days, instead of using tables in the back of your book, is just to use your calculator. So with the Casio calculator, that we recommend in your course, there are ways to handle the log. So in this case, if we follow the key sequence shown, we'll talk about in a minute, you can get the common logs on your calculator. So since 10 to the 0 equals 1 and 10 to the 1 equals 10, then the numbers between 1 and 10 have logs or exponents between 0 and 1. So there's that relationship. If we look at a value, 5.32 is equal to 10 taken to an exponent, which is a fractional exponent, 0.726, we see here that 7.63 equals 0.883. Okay, these values are all calculable on your calculator. So the logarithmic form then says that since the value log, notice there's an implied 10 there, of 5.32 is equal to 0.726. So if we want to find the log of 4.23, if we follow the keystrokes on the calculator, the first thing you're going to do is press the log key to put the calculator in logarithmic mode. When you do, you'll see it shows up on the screen. Enter the value 4.23, and when you hit then the equals key, the log value, in fact, shows up. Finding logarithms of numbers greater than 10. Key point, only numbers that are multiples of 10 will have logarithms that are whole numbers. So again, if we take a look at these values, what's the log of 50, 500, 5,000, 50,000? You can see that what happens when you take the log, and these just become shortcuts. There are values that you will use a lot, and these things will be inherent. You'll start to memorize them. The log of 50 is 1.699. You'll notice that the log of 500 is 2 zeros, 6.99. So the fractional portion remains the same. The whole number is the number of zeros. The whole number part depends then on the multiples of 10 contained in the number. So if we look at an example here, find the log of 37,500. The log of 37,500 then can be broken apart into the log of both of the factors. 3.75 times 10 to the fourth, if we use scientific notation, then the log of 3.75 can be added to the log of 10 to the fourth. So the log of 37,500 becomes the log of 3.75 plus 4. We know that because it's going to have 4 zeros. So if you take the log on your calculator of 3.75, you get 0.574. Add 4 to it, and you get 4.574. Move it back into an exponential form. 10 to the 4.574 equals 37.5. Logarithms less than 1. For any number less than 1, the logarithm or exponent now becomes a negative number. So that's the key, is to when are negatives invoked. So if we look at an example, find the log of 0.0275. It really becomes the log of that value becomes minus 1.561. So you can see it's a negative value. Again, you would put that in the calculator, and that's the value that would show up. We can take it apart to, using scientific notation. Again, these examples are showing you the long way to do this. You're not going to do it this way. You're going to use your calculator. So 2.75 times 10 to the minus 2. So if we break it apart into its two portions here, take the log of 2.75, take the log of minus 2. The log of minus 2 is minus 2. The log of 2.75 is 0.439. So when we add the values together, we end up with what your calculator would eventually show you, minus 1.561. Another example here. Again, the best thing to do is pull out your calculator and run through these. These long explanations are just for illustration, to show you how you could do this. Back in the days when you had to do it using the tables, this was more appropriate. Today we don't do it that way. Multiplication of numbers using logarithms. So in this case, we take a look at what we've previously learned about handling exponents. We notice that when we handle values that have exponents, 10 squared, if we want to multiply it times 10 to the third, the value becomes 10, the exponent 2 plus 3, which gives us 5. The same thing here, y to the third, the product of y to the fourth, y 4 plus 3, and the exponent becomes 7. So again, this is a refresher from what we covered early in the course. So using a value here just as an example, we can see that if we want to multiply 37 times 763 and use the log to calculate it, we can change it to base 10. So the log of 37, 1.568. The log of 763, 2.883. If we look at it exponentially, 10 to the 1.568 is 37, and the value here for 763. So the product then of 67 times 736 is, using the exponential forms, 10 to this fractional value, 10 to this fractional value, multiplied together, gives me 10 at 4.415. 10 to 4.415 is 282 times 10 to the fourth. Okay, so it's just a method of using the logarithmic values to calculate these products. So since we can use the rule that says the log of AB is equal to the log of A plus the log of B, we could put the problem together just exactly like this. Split the two terms up of 37 times 736, take the log of each value, and you would come up with the solution for that value, for the log of the product of that value. So if we take a look at an example here, if we have the product 7,600 times 230, we want to take the log of that. Again, we can turn it into an addition, add the two terms together. The log of 7,600 is 3.881. The log of 230 is 2.362, which gives us a value of 6.253. So if we sum the 2 points together, the two values together, this is our solution. Okay, again, and it goes back here to prove the values exponentially. Okay, same thing. We have a product of 1760 with a fractional value 0.0273. Again, we divide the two values up, log A, log B. We end up with our values for the logs of A and B becoming 3.246 added to a minus 1.564 gives us 1.682. Okay? So again, the demonstration below using the exponential forms. Division, again, we learned the rules for division using exponents. The examples here show that primarily, since we're using with the base the same value, whether it's 10, 8, or A, we handle the exponent the same way. We end up subtracting the value in the denominator, the exponential value in the denominator, from that in the numerator. So 10 to the 7 minus 4 gives us 10 to the third. Okay, so in this case, you'll notice a to the fifth, a to the minus third. When we move it into the numerator, it in essence becomes an addition. So we sum 5 and 3 and get 8. So to find the quotient using logs, again, find the log of both the numerator and denominator, the dividend and the divisor, if you will. Subtract the log of the divisor from the log of the dividend, and then change to exponential form. So in this case, we divide it up into the two terms. We take the difference in the two. We get a value of 1.544. 10 to the 1.544 is 2.85 times 10. Okay, same thing in the example down here where they're showing us how this plays out just using the exponential forms of each of the terms. Okay, so again, a lot of this you're going to do on the calculator if you use logarithms. Find the quotient of 1.73 divided by 96,700. Seems like a pretty ominous number with these fractions and very large numbers. But using the logs, you can simplify it. If I take the log of the numerator, take the log of the denominator, take the difference in the two, I end up with a value of minus 4.747. Put that into exponential form. 10 to the minus 4.747 gives me a value of 1.79 times 10 to the minus fifth. So that becomes the log of the product. Okay, same thing in the other example. Raising a number to a power using logarithms. Raising a number to a power, again, is the process of multiplication. In general, to find a to the x using logarithms, there's our relationship. Notice it's simply a matter of I take whatever the exponent is in the log portion, I move it down into in front of the log a value, take the product of the two. So in this case, let's find 4 to the fifth using logarithms. So we find the log of the number, we multiply the log by the exponent, and then we change it to exponential form. So the log of 4 to the 5th equals 5 times the log of 4. So log of 4 is 0.602. Multiply that times 5, I get 3.01. 10 to 3.01 gives me 1.02 times 10 to the third. Handling it exponentially along the bottom here, you can look at it. Again, this is something you would have to do on your calculator to handle those fractional exponents. Another example here, we're going to take a fractional number and cube it. So to find the log of that, we take the log of 0.0745 cubed. We're going to take the log of 0.0745 and we're going to multiply it times 3. So 3 times minus 1.128, which is the log of that value, we get minus 3.384. In the exponential form, if I take 10 to that exponential value, I get 4.13 times 10 to the minus 4. So if you do these examples on your calculator, you will become quite versed at taking logs on your calculator. At some point in your career here in your education, you'll take inverse logs, which is an interesting aspect as well. Finding the natural log then of a number. You'll notice that on the calculator, the keystrokes are using the ln key instead of the log key. Since the ln key is the natural log using the e as the base, where e is 2.72, again rounded, for values. This is primarily used in some higher order calculus where we take e to the values. We start using, again, Euler's relationships to solve. Something called the Laplace transform uses E a lot. In circuits, capacitors and inductors use E values to calculate some of the characteristics of the component. You can see here in logarithmic form and exponential form, the log of 5, 0.699, the natural log of 5, 1.609. So there is a difference in the value, so do not get those confused. So if we're asked to find the natural log of 5, again, the keystroke is hit the ln key. Once the display comes up, enter your value, 5, hit the equal key, and what will show up is the exponential value. So e to the 1.609 is 5 when we look at the relationships. Okay, so if we take a look at the last two examples here, the natural log of 45 is equal to 3.08. Run it through your calculator. E to 3.807 gives us back 45. As with common logarithms, the natural logs of numbers greater than 1 are positive, and the natural logs of numbers less than 1 are negative. We can use e as a number. I mean, it is a number. We know we've already shown that it's a number. But e to the 3.434 then is equal to 31. Again, you run it through your calculator. We can also square e. E squared is equal to 7.39. So logarithms. We're going to come back to those later when we start doing some of our graphing functions where logs are very important. Primarily frequency response and with power as well.